Okay, let's take a look at question number 3. So here's what we have. We have tetrafluoroboric acid, which is a strong acid with the formula of HBr4. The acid can be prepared by reacting with a weak acid, H3BO3. Oh, nice, they give us the molar mass here, with HF, and according to the equation before. Now, first thing that jumps out at me is notice this is HBF4. This is actually right here because this is an acid, and so what happens is the hydrogen is going to jump off of the HBF4, and we're going to find it right here. But we're going to be mainly dealing with BF3. Okay, so here's what is prepared. To prepare a solution of BF4, HF is bubbled into a solution containing 50 grams of H3BO3. So we've got 50 grams of this, and this says that this is being bubbled into a container. So this means that we have a lot of this. Okay, anytime you see something be bubbled into it, you really don't have a way for recording how much is being put in there. That's going to be our excess reactant. Okay, so I've got 50 grams of this being bubbled in, lots of this, and let's see, what does it ask us to do? It says calculate the maximum number of moles of BF4 that can be produced. Okay, so our question mark for I is going to be how much of this, and I'm going to put my units up here of moles, right? Which should make us happy because we don't have to do a whole lot of conversion there if that is in moles. So here we go. So I need to go from grams into moles of this, do our molar conversion, okay, and then get into moles of BF4 ion. So here we go. 50 grams times 1 mole over the molar mass. In this case, it's 61.83, which they gave to us. All right, and that's going to lead us to 0.8086689 moles of H3BO3. Now, check this out. So I've got this many moles of H3BO3, and this is a 1-to-1 ratio, which makes this answer super easy. I'm going to check it for sig figs real quick. I've got 1, 2, 3 here, 1, 2, 3, 4 here, so I'm going to put this answer in 3, okay, or 0.809 moles of BF4 ion. Okay? So now, but notice I left this up here. In my future calculations, I want to use this full number. Okay, this is a final destination. This is a final answer for I. Okay, and please label these so it's okay to do our sig figs there. But I like writing these out because I'm probably going to have to use that again later. All right, the next part is this: calculate the number of liters of HF gas measured at 273.1 atm will be consumed. Okay, so they kind of switched it up a little bit here because this gas is being bubbled in there, and they're just curious how much of that is going to be consumed. Well, you can start this a couple different places. I'm going to start here because this is already in moles and go from BF4 ion to HF. So here I have my 0.8086689 moles of BF4. And I'm going to multiply this by my molar ratio. So that means I have BF4, 1 mole of BF4, and to every 4 moles of HF. Okay, and this is asking me for the number of liters, and it gives us in standard conditions. This is really good because at standard conditions, 1 mole equals 22.4 liters of a gas. Okay, just like we taught. Later on, we did one example like this where we had to use the PV equals nRT. Okay, so this is for non-standard conditions that we use this, but we don't have to use that this time. I just pointed out for reference. And so we're going to multiply this by 1 mole of HF gas, equals 22.4 liters of HF gas. All right, and we get 72.5 liters of HF gas. And this is gas that has been used. Okay, give a nice box, put a letter on there. Okay, they like to see that stuff. It helps them draw their attention towards your answer. And labeled answers are happy answers. All right, that is it.